Welcome to the workshop on this beautiful sunny day. Not that you can tell. We want to take a look at the integral test today, and we'll use this as an example. We want to use the integral test to determine the convergence or divergence of the series. And the integral test says that if we have a function that can be evaluated at integer values to give us these, or natural number, positive integers, to give us these values, then we can integrate that function. So the first thing to do is to recognize that this can be written as the sum from n equals 1 to infinity of the natural log of n divided by the square root of n. You might think to yourself, well, doesn't that have an extra term in it at n equals 1? Yes and no. It does, but the natural log of 1 is 0, so you can think of this as 0 plus, and in which case there's no issue at all. Excellent. So then we would say, all right, for this function, if we let f of x be equal to the natural log of x divided by the square root of x, then this is a continuous function from 1 to infinity, and it is, let's see here, non-negative also from 1 to infinity. At 1 it's 0, that's no problem at all, but then it's non-negative, that is it's positive, and continuous. Those are the first two conditions that we need. But we also need that it is a decreasing function in order to use the integral test. So you want to notice here that f prime of x, actually here maybe we should notice first, or write this down, that it was positive and continuous, and then observe that the derivative of x, of course I can't figure that one out off the top of my head, but I did find it out already, so feel free to confirm that the derivative is 1 minus the natural log of x divided by x to the 3 halves. Now, of course, 1 minus natural log of x looks pretty good, only when you get to the natural log of e, though, right? Once you get to the natural log of e, then it's 1 minus 1. So for 1 and 2, it's actually increasing. All the way up to 3, it's increasing. After 3, then we have it's a decreasing function. So this is less than 0 for x greater than, let's see here, certainly for x greater than or equal to 4. We can go all the way down to e, actually, but considering we just want integer values, then we'll say 4, and that's okay. So how does this work out then? Well, the integral test says that we have to have that it's decreasing for all values. But if we were to ignore the first couple of values, then we could start when n is equal to 4 and when x is equal to 4, and we could determine the convergence of that series. But of course, if I just add in a couple more finite values, then it's still going to converge. So all I need is that eventually this function is decreasing, and once it is decreasing, we start there and use that integral. An important thing about the integral test is also that it doesn't actually tell us what the sum is. It just tells us if the series converges or diverges. Right? It does not tell us the sum, it only tells us convergence or divergence. All right, so that's okay. We'll start at 4. So then we need to determine the integral from 0 to infinity of our function, the natural log of x, divided by the square root of x. And if we want to evaluate this, to get this integral, we're of course going to need to use the techniques appropriate for an improper integral. That is, we're going to need to use limit and take the limit as b goes to infinity and of the integral from 4 to b. Okay, so you need to use improper integral techniques to evaluate an improper integral. But then furthermore, in order to evaluate this integral, we would have to use integration by parts. So handle the improper integral appropriately, and you will want to use integration by parts, and you'll find that the limit actually goes off to infinity. Okay, so the limit as b goes to infinity of the integral from 4 to infinity of the natural log of x over square root of x dx is equal to infinity. So the limit is infinite, which allows us to conclude that this integral diverges. Hence the integral from 4 to infinity of the natural log of x divided by square root x dx diverges. And the series, the sum from n equals 1 to infinity, the series that we're interested in here, natural log of n divided by square root n, also diverges. Again, the integral test says that if we can write our summation in terms of a function, our function, evaluating at the n values of n, 1, 2, 3, 4, and so on, giving us the values in our series, the terms in our series, then we can, if we have that, it's positive, continuous, and decreasing. So here this was decreasing. Then we can take the integral, and if the integral converges for this function, then this series will also converge. If the integral of this function diverges, then this series diverges. That's exactly what we found here. Similarly, if we had the opportunity where we wanted to evaluate an improper integral, we could also conclude convergence or divergence by discussing the convergence or divergence of the series. For the most part, the integral test is really only used in terms of determining if a series converges, so that's exactly what this example is. All right, we'll have one more example of taking a look at the integral test. We'll take a look at something where it does converge instead, so a nice little spoiler there for you. But I'll have that example up here shortly, so I'll see you guys back in the workshop very soon.